Okay, we want to now look at two special types of linear transformations. And we say those that are injective or those that are surjective. And that's not necessarily an exclusive or, right? So let's take a look at what these notions are. First, let's recall if we have a transformation T, a linear transformation, or just a transformation in general from Rn to Rm given by, or let's say with matrix A. So we have a linear transformation with matrix A, then the image of the transformation T was defined to be the set of vectors y and Rm such that y equals ax, right? What this means is the image of the transformation is a subset of the codomain such that all of those points are mapped from something, or there exists some other point that's mapping to Rm here, right? And so I drew the schematic here where you have like Rm, and then maybe inside Rm you have the image of T. And then if you have Rn here, and you're mapping Rn to Rm somehow by T, right? Then the image is all of those points that are hit, right? That's why we call it the target. If you want to think about this function as maybe like throwing darts from Rn to Rm, well, it picks up a dart in Rn and it throws it, and the collection of all the points that darts hit, that's called the image, right? And there may exist points in the codomain that are not in the image. That's called the co-kernel, by the way, but we won't be talking about the co-kernel really in this class. So why did we need to recall the definition of the image? Well, we're going to need that for surjectivity. But first, let's start with injectivity. So let's give a definition here. A linear transformation, say T from Rn to Rm, is injective or one-to-one, which we abbreviate as one-to-one like this, if we have the following criteria, that for 2 points, x1 and x2 in Rn, if we have that x1 is different from x2, then this implies that their image is different. So what is this saying? This is saying an equivalent way of saying this equivalently. This would be saying that T of x1 equals T of x2. Like say you have the image of two things that are the same point. Well, then this implies that x1 is the same as x2. And so what does this mean? Injectivity means that every point maps to a unique point. It doesn't claim that every point gets hit, but it does claim that every point maps to a unique point, right? So the map is 1-to-1. So let's look here at my little schematic. We have Rn, we have Rm. Inside of Rm, we have the image of your transformation. And then there are points here, right? And these points, let's say y1, y2, y3, y4. Let's say these are points in the image. Well, okay. For injectivity, maybe I don't want to talk about the image, right? let me talk about that for surjectivity. So let's say we have like some points here. So we have like y1, y2, y3, and y4. And then we have points x1, x2, and x3. Well, then a map that's 1-to-1 means that you could not have the following case. You could not have that x1 mapped to y1, but x2 also maps to y1. This is not injective, because it's not 1-to-1, right? This particular subset is 2-to-1 because we're taking x1, x2, and we're mapping it to the same point. So this is an example of something that's not injective. If you want something injective, let me keep backing up here. If you want something that is injective, then you have to map, like every point is mapped to a single point. There can be points that are missed here, right? Y3 isn't hit, quote unquote, in this case. It's not the image of any point, but that's not what's required for injectivity. The only thing that's required for injectivity is that every point maps uniquely, or every point in the image is mapped to from a unique point, right? And that's exactly what this criteria is saying. It's saying, well, if you're in the image such that x1 and x2 map to the same point, well, then that had to be, then x1 and x2 had to be the same point, right? That requirement is what it means to be injective. Now, let's see what it means to be surjective. T is surjective, or we say onto, if for every y in Rm, there exists some x in Rn such that T of x equals y. Now, this is the surjectivity criteria, right? The injectivity criteria was, so let me write that here. To show something is injective, this is what you have to show, right? This is the injectivity requirement, right? So if you want to prove that a map is injective, you need to prove this here. To prove that a map is surjective, you need to prove this here. Well, it's not just this, right? Let me, whoa. Really, it's all of this. And what does this mean? Like this for every y in Rn here. So if we look at our schematic, we have Rn, we have Rm. This means for every point in the codomain, there exists an x in the domain such that, so if we had like, you know, y1 here, x1, x2, et cetera, right? I won't label them all. But we require that every single point is mapped to from something. When we were looking at injectivity, we had something that wasn't mapped to, and it could still be injective. Now for surjectivity, everything has to be mapped to, but it doesn't have to be 1-to-1, right? So you could have something, like you could have 2 points mapping to the same point, that's fine. As long as every point is mapped to, it doesn't have to be mapped to uniquely, right? It just has to be mapped to. And what does this also mean? This then, if every point is hit by the map T, well, then this criteria here, this is the same as saying that the image of T is Rm, right? Because then everything in Rm is hit by something. So there are two ways to prove surjectivity. I mean, there are a bunch of ways to prove injectivity and surjectivity. As of right now, there are two ways that we would understand how to prove surjectivity. It would be to show this statement here, or it would be to show that the image is the entire codomain. Either way. Okay. So I have another proposition, or I have a proposition here about injective maps, and then I want to look at some examples here. So here's a proposition. T is injective. And remember, injective means one-to-one, if and only if. So if you ever see a double direction arrow, that means if and only if. Right? And logically, the statement if and only if means both directions imply one another, right? Like A implies B and B implies A. That's why we have the implication arrows in both directions here. So T is injective if and only if T of X equals 0 implies that X is 0. So let's see why this is necessarily true. Let's prove this. Well, to prove an if and only if statement, you have to prove the if, and you have to prove the and only if, right? And so really there are two proofs. You have to prove A implies B, and then you have to flip around and prove that B implies A. That's what it means for if and only if. So we're going to prove the if direction. And that means we're going to assume that T is injective. And then we want to prove that we want to prove the following statement, that T of X equals 0 implies X equals 0. Okay, so this is the direction that we're proving. We can assume injectivity, and then we have to prove this logical statement right here. So how can we prove this? Well, T is a linear transformation. And we know linear transformations send 0 to 0, right? Well, sure. If you have T of 0, then that's T of 0 plus 0, which is T of 0 plus T of 0. Well, and then you subtract T of 0 from both sides, and you get 0 equals T of 0, right? But now, we have that T of 0 equals 0. But then we assume, right, to prove this statement, we need to assume that T of X equals 0. So let's assume T of X equals 0. And then we would want to prove that X equals 0. Well, what do we have? We have that T of X equals 0 and T of 0 equals 0. So i.e. T of X equals T of 0. But what can we deduce from this? Well, this implies that X equals 0 since T is injective, right? What does the injectivity criteria say? It says that if you have 2 points in the image that are the same, then the points that they were mapped from are also the same. And so we have this now where we have 2 points in the image that are the same, right? T of X and T of 0. Well, then since T is injective, we know X and 0 have to be the same. And so we've proven then that if T is injective, that implies this implication, right? It's almost like embedded logic to imply an implication, but that's what we've done. And now we need to prove the other direction, right? Now we need to prove that let's start with the assumption. We now can assume that t of x equals 0 implies x equals 0. We can assume this, and we want to prove that t is 1-to-1, or t is injective. So how do we do that? Well, let's use this assumption. To prove that t is 1-to-1, what does that mean, right? This means we need to prove that t of u equals t of v implies u equals v. This is the same statement. Like if we can prove this statement here, then that's the same as proving t is 1-to-1. So how can we prove this? Well, we need to use our assumption somehow. And our assumption deals with t of something being equal to 0. And so we need to set something up so that we have our transformation of some element is equal to 0. Well, how can we do that? Well, if we start, let's take tu equals tv, right? We can start here. Well, this implies that tu minus tv is equal to 0. But t is a linear transformation. So this implies that t of u minus v is equal to 0, right? And this is because t is a linear transformation, and we have the linear transformations split over addition and subtraction. But now we have this assumption up here, right? That if t of x equals 0, well, then that implies that x equals 0. But we have that t of uv equals 0. So that must imply that u minus v equals 0, which implies that u equals v, which means if we started with the assumption that tu equals tv and ended at the assumption u equals v, this implies t is 1-to-1 QED, right? And so we want to be able to start looking at using injectivity and being able to prove properties of injectivity. And so now, because we have this proposition to show injectivity, it suffices to show this here. This is kind of a new injectivity requirement, right? Because we now know that this statement is identical to the statement that if 2 points in the image are the same, then they're the same in the domain. Cool. Let's do an example here. Let's look at a transformation t from R2 to R2 given by t of xy equals 1, 1, 1, 2 xy. And we're given that this is linear, right? It's represented by a matrix. Therefore, it has to be linear because we know that those are one and the same. And let's ask ourselves, is this transformation onto? Is it 1-to-1? And so let's check. Let's see. Well, let's start with onto or surjective, right? What do we need to show? We need to show that for all points A, B in R2, and we're looking in the target R2 here, right? We need to show that there exists X and Y in the source R2 such that 1, 1, 1, 2 of xy equals AB, right? That's exactly what it means to be surjective. It means for every point in the image. And what is the image, right? The image is what you get after applying the transformation. And so the result of this transformation is going to be some vector. And so we want to show that for every vector in R2, there exists an XY such that this equality holds. That's what it means to prove surjectivity here. Well, then in that case, proving surjectivity is identical to saying, so here then, surjectivity is the same as this system having a solution for all A, B in R2, right? Because if there's no solution for some value of A and B, well, then that's a point in R2 or a vector in R2 that's not being hit by this transformation. So we know how to solve this system, right? In this case, proving surjectivity is the same as solving this system. Well, we can solve this system pretty easily, right? We set up the augmented matrix 1, 1, 1, 2, A, B. And pretty quickly, we see if we take row 2 and replace it with row 2 minus row 1, we're going to get 1, 1, A, 0, 1, B minus A. And then we would take, for the next step, it looks like we need row 1 to be equal to row 1 minus row 2. And if we do that, we're going to get 1, 0, 0, 1. And then we'll have B minus A on the bottom. And then we're subtracting. So we would have A minus a negative A. So that would be 2A, right? So we're going to get 2A, but then we're subtracting B. So that would be 2A minus B, which means here we have a solution set of XY equals 2A minus B, B minus A. Well, the domain here, this is a solution for all real numbers, A and B. And because this holds for all A and B, right, this implies that T is onto. Now, if it weren't onto, you would find some values A and B where a solution could never happen, right? Like maybe you end up with a solution where you're dividing by A. Well, and then A couldn't be 0, right? And then in that case, you would be missing a point. And so there's no surjectivity. Or if you could only have negative numbers or positive numbers, right? Then there would be points in the image that, or excuse me, there would be points in the codomain that are not in the image. And because of that, you wouldn't be onto. So we've proven onto. Now let's prove one-to-one or injectivity. So what do we need to show injectivity? Well, let's use this new criteria that we've proven here. We just need to show that the image, like if the image of a point is 0, then that point was 0 itself. So what would we need to set up? We would want to show that if we had 1, 1, 1, 2, x, y, if this is equal to 0, 0, right? If the transformation of the point is equal to 0, then we need to show that this implies x, y equals 0, 0. Well, what you can do is you could resolve this system with A equals B equals 0. But we've done that, right? We have the solutions. But now we just look at when A equals B equals 0. Well, that implies that XY equals 0, 0. So that implies that T is 1-to-1, right? And again, if you were to go through this construction and then find that there exists a solution where X and Y are not 0, right? Like if your system does not have a unique solution of 0, 0, when you're solving it equal to 0, well, then that means it's not injective, right? This criteria that T of X equals 0 implies X equals 0. that means that the system that you set up necessarily has a unique solution of 0, 0. If you can construct a non-zero solution to that, then the transformation is not injective or not one-to-one. And so in this case, what we've found is we found a function that is both onto and one-to-one. And that's a special type of function that we call an isomorphism. And we'll talk about isomorphisms more. Those are quote unquote the most important type, is they behave very nicely. They're one-to-one and onto. So we'll dedicate an entire day or most of a day to looking at isomorphisms. But I do have kind of a homework for you here. I want you to find an example of a linear transformation that is first not one-to-one or onto. So I want you to find a linear transformation that's not one-to-one and is at the same time not onto. I want you to find one that is one-to-one but not onto. I want you to find one that is onto but not one-to-one. And I want you to find one that is both one-to-one and onto. Not the last example. Okay, so here, that's an example of an isomorphism, right? Something that's one-to-one and onto. But I want you to find a different one. And so if you can find these examples and really understand, right, it helps to understand what an injective map is when you understand what an ejective map isn't, right? And so these kinds of examples will help you. And same with surjective, right? These examples will help you to understand, hopefully, injective and surjective maps, kind of how they're behaving. All right, here's a theorem that is worth stating here. I won't prove it, but if we have a linear transformation T from Rn to Rm with matrix A, then we have two statements. We have that T is injective if and only if the rank of A is n, which is the dimension of the domain, just to note. And then T is surjective if and only if the rank of A is the dimension of the codomain, which is also, since it's injective, it's the dimension of the image, but I'll say of the codomain, right? Surjective maps, the image of the map is the entire codomain. Okay, and lastly, I want to make a remark about the composition of injective and surjective functions. Let's say we have two linear transformations. First, we have a linear transformation T from Rk to Rm, and then S from Rn, sorry. Yeah, let's say M to Rn. Then there are two statements. The first is that if T and S are onto, this implies that S composed T is onto. And second, you can probably guess, if T and S are one-to-one, this implies that S composed T is one-to-one. So the composition of injective functions is injective, and the composition of surjective functions is surjective. Let's prove it. Let's start with the onto case, right? What do we need to show? We want to show that for every point Z in Rn, there exists an X in Rk such that S of T of X equals Z, right? That is the surjective criteria. It means for every point in the image, there exists a point in the domain such that that point that we started with is mapped to from some point in the domain. So how could we show this? Well, what do we start with? Well, we're starting with some element in the domain of the composition, right? Because remember, the composition is a map from RK to Rn. This is S composed T, because it's T first and then S. So let's start with Z in Rn. Where can we go from here? Well, S is onto. What does that mean? That means there exists a Y in Rm such that S of Y equals Z. That's exactly what it means for S to be onto. That's the definition of surjectivity for the map S. Okay, but then what? Well, we also have that T is onto, right? By assumption. That implies there exists an X in RK such that T of X equals Y. Well, then let's look at the formula S of Y equals Z. Well, if there exists a Y or exists an X such that T of X equals Y, well, then this implies that S of T of X equals Z. And now we've shown that for every Z in Rn, we can find a point X such that S of T of X is equal to Z. So that's proven surjectivity, right? If you have two, this implies here that S composed T is onto. Okay, next let's prove that if S and T are injective, then the composition is injective. So what do we want to show for injectivity? Here's the second one. We want to show that S of T of X equals 0 implies X equals 0, right? That was our new requirement, or our updated requirement to showing injectivity, was to show that if the transformation of some point is 0, well, then that original point had to be 0. Okay, well, what do we know? We know that S is 1-to-1. And this means, what does that mean? That means that S of T of X equals 0 implies that T of X equals 0, right? That's exactly what it means for S to be injective. But now we have T of X equals 0, but T is 1-to-1, not H. T is 1-to-1. So T of X being 0 implies that X is 0, which gives us the injectivity property of the composition. So this would tell us, like, therefore, S composed T is, or let's say S composed T of 0 is 0. Therefore, the composition is injective. Okay, so this is all I wanted to talk about for injective and surjective functions. And in the next video, probably next Monday, we'll start to look at the case when a map is both injective and surjective, and we call those isomorphisms.